Okay, should I? Okay, all right. So I wanted to. So the second lecture of today, I want to talk about Kähler surfaces and what happens to the Kähler-Ricci flow. But to do that, I need a little bit of sort of background on line bundles, etc., and some terminology from algebraic geometry, and then I'll explain the behavior of the Kähler-Ricci flow. Kind of overview. Okay, so let me. So in complex dimension 2, there's a key new difficulty that we didn't see in dimension 1. Is the presence of blow-ups. So we have what's called the blow. This construction of blowing up a point and getting a new manifold. And so using blow-ups, you can get we get lots of manifolds in some sense. We get many manifolds, many more manifolds. So let me just explain. So I think this is probably familiar to many of you, but maybe not all of you. So let me describe the let me go over here. Well, maybe I can fit it in. The blow up of let me start with C2. I'm going to work in two complex dimensions. This is the blow up of C2 at 0. And what is it? Well, it's you take pairs ZL, where Z is an element of C2 and L is an element of P1. So I think of L as an element of P1, but these remember these are the lines in C2 with the property that Z is in L. So since these are the lines in C2, I can think it makes sense to say that Z lies in the line L. And there's a map. So this of course has three dimensions, but this is one algebraic equation, so this is a two-dimensional manifold. And there's a map pi, called the blowdown map, which maps this blow-up of C2 at the origin to C2, and it's simply the projection. So ZL goes to Z, and this map is an isomorphism. So it's a biholomorphism outside pi minus 1 of 0. So why is that? That's because each element of C2 lies in a unique line, with the exception of the origin, because the origin lies in every line. And the origin is that this actually gives you this we call E, and this is a copy of P1. So so 0 cross P1 gives you a whole P1, and this has a name. So E is called the exceptional curve. The exceptional curve of pi. Okay, and then so what I've done is I've created a new manifold, and then we can do this for any M. We can do this for any Kähler surface. So this was not compact, but I could do it for any compact Kähler surface M, and get the blow up of M at a point P. So P is a point in M. And it turns out that this will be a new Kähler surface. And it will have more topology than the original one. It'll have an extra E, exceptional curve, which is like a P1 inside it. So this gives us a way to create a lot more manifolds. And it's not an operation that was available to us in one dimension. Okay. So now I want to explain, I want to give a little bit of terminology and notations on about line bundles and pairings and so on. So I'm going to need a little bit of background from algebraic geometry. So let me just be brief. So a line bundle. Of course, I mean a holomorphic line bundle. Holomorphic line bundle, L over M, let's take M to be a Kähler surface, is given by a set of, I want to think of it as being a set of transition functions, T alpha beta, where T alpha beta are maps from U alpha intersection U beta to C star. So I should say, given by T alpha beta, these are the transition maps, and U alpha is a open cover of M. Where these are holomorphic. And such that they satisfy that T alpha beta, T beta alpha is 1, and T alpha beta, T beta gamma is T alpha gamma. Okay. So they have to satisfy those conditions. And then we can say that the T alpha beta is the same as T, say, prime alpha beta if you can write T alpha beta as T prime alpha beta times F alpha over F beta, where the F alpha maps from U alpha to C star holomorphic. So there's a notion of equivalence of line bundles. Well, strictly speaking, you also need to be able to go to refinements of covers, but I'm not going to get into that. So I'm thinking of a line bundle as being the set of these are transition maps. Transition maps plus the open cover, just in the same way as you think of a manifold as being coordinate changes plus open cover. And then a section, or a holomorphic section, I should say, holomorphic section S of L is a collection S alpha maps from U alpha to C, which are holomorphic, such that that S alpha is equal to T alpha beta S beta on the overlaps U alpha intersection U beta. Okay. Well, another important concept that we need is the notion of a metric, or Hermitian metric. So when I say Hermitian metric on a line bundle, it's different from a Hermitian metric on a manifold. So Hermitian metric on L, which I'll call H, is a collection of functions from U alpha to the positive reals, such that it also satisfies some condition, which is involving the transition function. So these are smooth maps, they're not holomorphic. It satisfies this transition property, this coordinate change property. And then you can see that the norm, you can take now the norm of a section, which is defined to be H alpha, S beta bar. This is now well-defined, independent of chart. Well-defined, independent of chart. Right, this is independent of the choice of coordinate chart. So this is actually forced by this definition. So this is the norm of a section. So from these two, you get that this is well defined. And then we can talk about the curvature of H is by definition RH, and again I'm going to put in a 2 pi is dd bar log of H alpha. And then that's well defined, independent of chart, because if you change chart, I keep doing that. If you change chart, then you see that you differ by this norm squared of a non-vanishing holomorphic function. But it's the fact that dd bar log of the norm squared of a holomorphic non-vanishing function is 0. So it's well defined, independent of chart. And then we define the first Chern class. We define the first Chern class of L to be, so this is C1 of L, it's simply the cohomology class of RH. And this is an element of H11. And it's independent of the choice of H, which is easy to see. Independent of the choice of H. And you might ask, well, how does it coincide with the other notion of, how does it correspond to the other notion of first Chern class that I was talking about? Well, that's a special case where you take L, a very special L. So notice that so on any complex manifold M, on any M, we have what's called the canonical bundle. We have the canonical line bundle. The canonical line bundle Km, let's call it, with the transition functions T alpha beta given by, what you do is you just look at the coordinate changes. So take dz alpha, dz beta. So we have, coordinates z alpha 1, z alpha n would be coordinates on u alpha, and then z beta would be coordinates on u beta, and then you can look at the determinant of that. That's an n by n matrix. You look at the determinant. It's holomorphic because the coordinate changes are always holomorphic. So this, maybe I got that the wrong way around. Sorry, it should be beta alpha. I always get that wrong. This defines this certainly satisfies these conditions. You can easily check. It's non-vanishing because these are genuine coordinate changes. And so that's called the canonical line bundle. And then we could define a metric on that. We can define a Hermitian metric on the fibers of the line bundle. And that is defined by H alpha. So I just have to define on each U alpha. And it's given by what's the determinant. You take the determinant of Gij bar in the alpha, and then you have to take the inverse. And then this has okay, where G is a Kähler metric. In fact, you could actually take G to be a Hermitian metric. It would also work. And then notice that then notice that the curvature is nothing other than dd bar log of determinant of G. There's a minus which cancels that minus because there's a minus here. Then I have another minus, and so what we see is that the first Chern class of Km is given by the cohomology class. I guess it's a factor 2 pi. Is given by this. But this was minus the Ricci curvature. So this is minus the Ricci curvature of omega, which is minus C1 of n. So the first Chern class of the manifold is negative, the first Chern class of the canonical line bundle. There's an operation that we can do, of course, on line bundles, and that is we can take tensor powers. So note that. So if you're given line bundles, say L and L tilde, you can define. I prefer that maybe we'll use the additive notation L plus L tilde, or you can use the multiplicative L times L tilde to be the line bundle where you just multiply the transition functions with transition functions. You just t alpha beta, t tilde alpha beta. So where this is given by t alpha beta, and this by t tilde alpha beta. And then similarly, you can raise to the power. So we can define ml, or you can also call it L to the m. So there's two different notations for the same thing. This would you just take t alpha beta, you just raise it to the power m. So in particular, you can talk about L inverse or minus L, where you just take 1 over the transition function. And then notice that if you take the first Chern class of, say, m times L, that's the same as m times the first Chern class, etc. Okay, so let me not go into any more detail. Okay, so this is some basic terminology I'm going to be using. Now let me say something about the intersection pairing. Which I'm going to be using rather a lot. So if you're given cohomology classes alpha and beta, we can define. I'll write it alpha dot beta. That pairing, just to be. This is just the product. You just take. Let's call it, say, alpha naught wedge beta naught, where you integrate over m. Each one is a 1-1 form. When you wedge them together, you get a top-dimensional form. It's a 2-2 form. You can integrate that over a Kähler surface m, where here alpha naught is any element of alpha, and beta naught is any element of beta. So alpha naught and beta naught are closed 1-1 forms. Right, so these are closed 1-1 forms. Well, we can then define, so given line bundles L and L tilde, you can define the product L dot L tilde to be just C1 of L dot C1 of L tilde. And this will actually give you an integer, if I get my factors of 2 pi correct. And moreover, suppose you're given a, so I'm going to talk a little bit about topology. Given a curve C on M, so this is a one-dimensional analytic subvariety. So this is a one-dimensional analytic subvariety. It could, technically speaking, I could allow it to have some singularities, but those will be just at some points. But mostly we're going to be dealing with curves which are smooth. So there'll be genuine complex submanifolds of complex dimension 1. So given a curve C on M, which is defined, so by being an analytic subvariety, it means it's locally defined by the vanishing of analytic function. Defined by f of alpha is 0 on u alpha. So here, so vanishing at order 1, vanishing at order 1. along C. So F alpha is vanishing order 1 along C. And then it turns out, given that data, you can define a line bundle. So we can define a line bundle which I'll write as C with the square brackets around. So I guess that's a little bit confusing with the cohomology class, but well, that's the notation I'm going to use. By simply T alpha beta is F of alpha over F of beta. So that defines for me a line bundle associated to a curve C, and then I can define objects like L dot C, which would just be C1 of L dot C1 of C. Because now it's a line bundle, I can talk about its first term class and so on. And C dot C tilde, which would be C1 of C dot C1 of C tilde. And again, these would be integers. And so these are these so-called intersection numbers. Well, let me mention a couple of important points. One is that so note. The first one is that there's by Poincare duality, it turns out that if C1, so C and C tilde, are distinct curves, then C dot C tilde, that intersection really is the number of intersection points. The number of intersection points of C and C tilde. He wants to check that all these things are well defined. I claim that it is. The other thing to note is something called the Poincare-Lalonde formula, which is going to be very useful. Poincare-Lalonde. And what this says is that if S is a holomorphic section of a line bundle L, where L, let's say, has a Hermitian metric H, and S vanishes along, I don't know what I want to call it C, I'm going to call it D, because it could be that D is maybe has sort of, when I talk about curves, I always want my curves to be irreducible. I really want this. I'm going to take it to be irreducible when I talk about curves. Whereas this D, in theory, might not be. Then if you look at minus dd bar log of S squared H, this is just R of H plus, this is plus, and this is minus, plus what I'm going to write as T of D, where this T of D is the current of integration. Current of integration along D. Along D. And then that tells you something, because it tells you that actually L dot C, which is by definition just the integral of R of HL, wedge R of HC, if you like, what it tells you is that if you take this D to be the C corresponding to L, then this is just the R of H corresponding to C, and then this just becomes T of C. And then this becomes nothing other than just the integral of RH over C. Because what happens is that this now just becomes the current of integration. And then by definition, you just get the integral over C of this 114. What happens to this? Well, this disappears because it's dd bar exact. And so you're integrating against closed things, so you integrate by paths. You might worry because this thing is singular, but it's only a log, so it's still integrable. That's fine. Okay. All right, so there's some very rapid introduction to line bundles and curves. And so I'm going to use this stuff a lot, so that's why I wanted to go into the details. Okay. So let me also just mention what is the relation with these exceptional curves. So the relation with E, the exceptional curve of a blow-up. Of a blow-up. Well, it turns out that it turns out that E is is what's called a -1 curve. Is a -1 curve, which means that E, which we know is a smooth curve, biholomorphic to to P1. We know that already, but moreover, that E dot E is equal to -1. So in other words, it has self-intersection -1. Self-intersection -1. Well, how does a curve intersect itself? Well, we don't need to worry about that because we have a definition. So we don't need to worry about what that means geometrically. We can just say, well, by definition, E dot E is simply the integral over E of R of H of E, where HE is a metric on the line bundle associated to E. And then you can just do the computation, and it's actually just do the computation with sort of simple exercise of the blow-up of the origin in C2, and what you get is the integral over P1 of the Fubini study metric with a minus sign, and it turns out to be, you get -1. But then a key point is that actually the converse is true. So conversely, if we're given E, a curve, a smooth curve, so biholomorphic to P1 inside a Kähler surface M with self-intersection equal to -1, then it is the exceptional curve of a blow-up. Then it is the exceptional curve of a blow-up. Of a blow-up. So in other words, there exists a map pi from M to N, which blows down E, if you like, which blows down E to a point on N. So M is the blow-up of N at some point, and E is the exceptional curve of that blow-up. Okay. So all right. So maybe I have one last definition to give, and that's the Coderre dimension, and then I can actually go back to talking about the Coderre-Ricci flow. Okay. So I want to talk about the Coderre-Ricci flow on surfaces, but so in the case of Riemann surfaces, we saw that the behavior depends on the genus. Now we want some kind of invariant on complex surfaces or Kähler surfaces. And since we have this operation of blow-ups, we want something which actually is invariant under blow-ups. And that's the Coderre dimension. So I want to talk about the Coderre dimension. So this is an important invariant, not just of Kähler surfaces, but of any complex manifold. And this is how it's defined. So here's the theorem / definition. What it says is that so M. Let's take M as a Kähler surface. Otherwise, you could define it much more generally. Then what we want to do is look at the dimension of the space of sections of Km to the power L. So this is this H0 called, this is the space of sections, the vector space over C, right? Vector space of sections, holomorphic sections of Km to the L. And L is going to be a large positive number. Now the theorem says that this is always, as L for L large, this is always of the order either L squared or L, or it's just going to be bounded and non-zero, or it's going to be just always zero. It's going to be always all zero. Okay, so there's 4 different cases. So they're going to be all zeros. The last one means that they're all zeros. Here they're all bounded as L gets large, and at least one of them is non-zero. In this case, we say that the Coderre dimension of M is equal to 2. Here we say the Coderre dimension is equal to 1. Here it's 0. So think of these as the power of L. The power of L is 2, 1, 0. And in this one we take to be negative infinity. Negative infinity. Okay. So we have this, again, it's just a definition. What's important about it, about this number, as I said, is it's an invariant, it's what's called a birational invariant. So it turns out that, so an important theorem again, is that the Coderre dimension of the blow-up of M at a point is the same as the Coderre dimension of M. That's a non-obvious fact. Okay. All right, so this notion has something to do with the ampleness of the canonical bundle. Let me not say anything more about that. So it turns out actually that most manifolds, sort of morally speaking, most manifolds live up here. This is a sort of relatively small class and simple class of Kähler surfaces. And what I want to do first of all is just exclude these. So let's go back to the behavior. I want to now talk about the behavior of the Kähler-Ricci flow. And I want to exclude this last case. So now let M be a Kähler surface. Kähler surface. And let's exclude the case where you have no sections of Km. Coderre dimension of M is not equal to minus infinity. And now I want to say what happens to the flow. So first of all, so M may have, let me just draw a picture. M, or maybe I need to, let me go over to that board. I need a bit more space. So M may have some -1 curves. Okay, so here's a picture. Here's M. It has Coderre dimension negative infinity, and it may have some -1 curves. which I think of as P1s. I don't know how to draw them really. I'll just sort of draw them as, I don't know, squiggles. Okay, these are my my minus 1 curves, if you like. This is E1, E2, and so on. I might have a whole bunch of these. I could draw them as little spheres, if you like. An algebraic geometer would probably draw them more like this. So M has some minus 1 curves. So remember, what are they? These are. Well, I guess I erased it. These are rational curves. They're P1s sitting inside my manifold, and they have this self-intersection minus 1, which means that there exist blowdown maps. And now let's say that we have a Coderre metric, and we want to ask, well, what happens to the Coderre-Ricci flow? Right, so what happens to omega t solving the Coderre-Ricci flow? dt of omega is minus Ricci of omega, where omega 0 is omega naught. Okay, so what happens? Well, it turns out that let me just sort of say schematically what happens. As t goes to some finite time t, as t goes to some finite time capital T, the Coderre-Ricci flow develops a singularity. So we have a singularity, but then what happens is that, I don't know why I'm drawing it differently, let me draw it like the same thing. What happens is that finitely many of these minus 1 curves contract away. So as t goes to capital T less than infinity, so the Coderre-Ricci flow has a singularity at t equals capital T. And what happens is that finitely many disjoint minus 1 curves contract away. Let's say they contract away. And what we get is some kind of metric omega t, which is singular. So we get omega t as a singular metric. Let's call this, say, M1 on M1. Let's say, yeah, okay. But then you might ask, well, can you start the flow starting from that singular metric? And it turns out you can. So this is a singular metric, but we can start the Coderre-Ricci flow again. We can start the Coderre-Ricci flow from omega t, and it immediately becomes smooth. It immediately becomes smooth, and then the same thing happens. We now have a smooth metric on a Kähler surface with a whole bunch of minus 1 curves, and after some finite time, as t goes to t1, say, some number of these minus 1 curves, the same thing happens. Same thing happens. That the minus 1 curves kind of contract away, and you end up with another metric which is singular on this space, which I'll call, say, M2. And then that process continues finitely many times, until you get an M, what do I call it, ML, say? No, not ML. I'll use K there, Mn, which has no -1 curves. No -1 curves. Well, in fact, let me call this M min. Because a surface with no -1 curves is called minimal. It's called a minimal surface. Okay. I've been a little bit vague here, right? Because I haven't really. I've sort of used the quote say they contract away. What does that mean? So let me say in words what happens. So first of all, so here M min has no minus. Is called a minimal surface. So minimal surface in the sense of algebraic geometry. It means it has no -1 curves. Okay, this means it has no -1 curves. So we started off with a surface with a whole bunch of them, and the Coderre-Ricci flow got rid of them piece by piece until there were none left. So what do I mean by it contracts them away? Because the Coderre-Ricci flow is simply a flow of metrics on a given fixed manifold. So what does it mean that we're changing manifolds? What I mean is that, of course, there's a map from this manifold to this manifold, because this one is just the contraction of a finite number of these guys, disjoint ones. So there is a map, and that map is a biholomorphism outside those -1 curves that get contracted. And what we get is we get metrics here, omega t, and then what we can show. So I should say that this is joint work with Jan Song. We did it quite a few years ago. This is not very new. What we show is that omega t will converge smoothly to some metric omega t, which has some singularities on finite number of disjoint -1 curves. But then you can identify it with a metric on this space here, where you blow them down. And then what we can show is that these metric spaces actually converge to this metric space in the sense of Gromov-Hausdorff. So what we get is smooth convergence outside these finitely many disjoint -1 curves, and we get global convergence in the sense of metric spaces. So that's what we prove. Okay. So in some that's yeah. So anyway, the basic picture is that the Coderre-Ricci flow is simplifying the manifold by removing these -1 curves. Each time you're kind of simplifying the topology, you're getting rid of these P1s until you have this minimal surface which has no -1 curves. And then let me.
So in the end, the metric is a metric space or is also a smooth metric?
It's a smooth metric, yeah, because at each step you get omega t, which is a singular Kähler metric. It's just singular at a bunch of points. It's a singular in a kind of harmless way. And immediately it becomes smooth. So there's a sort of canonical way to just continue it, and you get the smooth Kähler metric. Now, on what happens on this M min? So on M min, the Kähler-Ricci flow will exist for all time. Exist for all time. I'm making an assumption here which is about the Coderre dimension. If it's a negative infinity, it's very, this in general will not be true. On M min, the Coderre flow will exist for all time, and then what will happen? Well, what happens depends on the Coderre dimension. If the Coderre dimension is 2, so this more or less corresponds to the case of first Chern class being negative. And so this, what happens is that this is a little bit like the case of curves of genus bigger than 1. When you renormalize the flow, so the volume of this will go to infinity, so you renormalize, so the volume remains bounded, so you consider this flow, this will exist for all time, and as t goes to infinity, omega t will converge smoothly to omega infinity which is Kähler-Einstein. Okay, this is due to Huaidong Cao, except that That's in the nice case where the first Chern class is negative. So that's the sort of the nicer case. But there's a slightly nastier case where this might have singularities with possible Orbifold singularities. I'm not going to get into this. Orbifold singularities. And that case was dealt with by Tsuji and Tianzhang. So that's so you get but more or less you get a Kähler-Einstein metric, a metric where the Ricci curvature is equal to a multiple of the metric. Then there's the case that when the Coderre dimension is equal to 1, and this was proved by Song Tian. That again you do the same thing, same normalization, and the omega t converges to omega. Well, it's a bit more complicated since I'm running out of time. Let me just say you get a twisted Kähler-Einstein metric on a one-dimensional manifold on a Riemann surface. So what happens here is that the manifold actually collapses as t goes to infinity. Well, actually Strong and Tian didn't really prove that it collapses in the metric sense in general. They get this collapse in the sense of currents. So there's some open questions there about exactly what happens. And then there's the last case. Let me go over here. Is the case where Coderre dimension is equal to 0. And in this case, it's rather nice. You just look at the regular Kähler-Ricci flow, ddt, the unnormalized Kähler-Ricci flow. And then again, this is due to Weidong-Zhao, that omega t converges smoothly to omega infinity with Ricci of omega infinity is 0. So this is a so-called Calabi-Yau metric, or Ricci Calabi-Yau metric, or Ricci flat metric. So the basic picture is quite nice, that as long as we assume this, then the Kähler-Ricci flow blows down, contracts these minus 1 curves, simplifies the manifold, and then as t goes to infinity, as long as you normalize it correctly, it converges to a Kähler-Einstein metric. Well, modular a couple of technicalities. One is that you can have some singularities, but not too bad. In this case, it's a little bit messed up actually, because what you get here, this is what's called elliptic surface. You get a fibration where the fibers are elliptic curves over a Riemann surface, and the final metric in the end will sort of remember the original fibration a little bit. That's a little bit more complicated. Okay, so maybe that's a good place to stop. Thanks.
You don't assume Coderre as a mass, then maybe finite. T maybe finite.
Then t will always be finite. Even if you're minimal, it will still be finite. So what can happen actually will depend on the cohomology class. So one example is you could take P2 blown up at one point. That would have Coderre dimension negative infinity. One possibility is that has a minus 1 curve. One possibility is that minus 1 curve contracts. But another possibility is that P2 blown up at one point has a Kähler-Ricci soliton. You might just converge to that soliton after rescaling. But there's another third possibility, which is that P2 blown up at one point, it is also a ruled surface. So it's also a ruled surface over P1. And the fibers of that ruled surface may collapse, and you might get a P1, actually. So there are three possible different behaviors in that case. So that's why it's a little bit complicated. Maybe I'll talk about it some other time.
So you hope that being the Coderre one case, that convergence might be in better sense.
It should, yeah. So they get converged. The problem is that you have these multiple fibers, these singular fibers, and I don't know what really the right notion is actually for convergence. So you can get convergence away from those on compact subsets, but what happens there is not that clear.
tomorrow with
Okay.
tomorrow 4 p.m.
Wait, I get off a video on 10 tomorrow morning. So let's have a
Well, and Wednesday,